For this in-class problem, we're going to review how to use Raoult's law to analyze the vapor-liquid equilibrium behavior of a mixture. And so in this problem, what we're asked to do is we're asked to determine the temperature and vapor phase mole fraction of a mixture of benzene and toluene that's 26 by mole percent benzene in the liquid phase specifically, and also the total system pressure is 101.3. And the problem tells us to model the system using Raoult's law. And so based on this description, what I want you to do is I want you to pause the video here, and I want you to kind of sketch out a diagram of the system. Okay, so based on this problem description, we could sketch out, a very simple system that looks like this. So in our system, we have a liquid and a vapor phase, and in each phase, we have some composition of benzene and some composition of the toluene as well. We're told that in the liquid phase, the benzene composition is 0.26, and that the total system pressure is 101.3 kilopascals, and for later on, I'm going to convert that into millimeters of mercury. So that's 760 millimeters of mercury. And what we want to figure out is we want to figure out the temperature of the system and also the vapor phase mole fraction of the benzene. Okay? And so essentially in this problem, we have the liquid phase composition of the benzene. And we also know that x1 plus x2 is equal to 1. So that also gives us x2 if we wanted it as well. In any case, we have the liquid phase mole fraction, and what we want to find is the temperature that corresponds to that liquid phase mole fraction. All right? And so essentially, since we have the liquid phase mole fraction, what we want to find is the bubble point temperature. Right? So if we change the temperature of the system, what's the temperature going to be in which the first bubble of vapor forms in our system? That's essentially what we want to find. Okay? And so to do this analysis, we're going to use a combination of various named laws that you learned about all the way back in MEB 1. So the first law that we want to employ is Dalton's law. And so here, what Dalton's law tells us is that the total pressure of the system is going to be equal to the sum of the partial pressures of species 1 and species 2. So that's just what we get from Dalton's law. The next law that we should use is Raoult's law. And what Raoult's law tells us is that the partial pressure of species 1 in the system, so the partial pressure in the vapor phase, how much of the total pressure is caused by species 1, that partial pressure is going to be related to the composition of the liquid phase via this equation. And similarly, we could write this equation for P2. And we know, as I mentioned before, we could rewrite x2 in terms of x1. So taking these two named laws, what we could do is we could combine them. Into this equation. So the total P of the system is equal to x1 P1 sat plus 1 minus x1 P2 sat. All right? And so we know this, and we know this as well. But what we don't know off the bat is what P1 sat and P2 sat are. And the reason for that is we know that P1 and P2 sat, those are going to be functions of temperature only. In fact, we can model P1 and P2 sat using another named equation Specifically, we could use Antoine's equation, where generally your pi sat is going to be equal to 10 raised to some constant minus another constant over t plus c, which is another constant. Okay? And so depending on the chemical species that you're talking about, these constants are going to be different. And so what we could do is we could go back to our combined Dalton and Raoult's law, and we could plug in. A2 minus B2 T plus C2. Okay? And now, in the way we have this equation written out, which I'll call equation 1, we only have one unknown, which is that temperature value. Okay? I'll talk about how to get that in a bit, but in any case, we also have these constants that we need to deal with. And the way we could figure out those constants is we could just look them up. And so if you remember from your Mass and Energy Balance 2 book, the Felder, Rousseau, and Bullard, so that's the MEB textbook, in one of the appendices, it actually just lists the Antoine's equation constants for various chemicals. And so in the constants that they list, the temperature that you would plug in would be in degrees Celsius, and the pressure that you would get back out would be in millimeters of mercury. Hence why I did that unit conversion earlier. In any case, if we look up in the back of that textbook, we find these values for the benzene, and we find these values for toluene. Okay. Alright, so if we go back to equation 1, we now know all the constant values. We know the pressure and we know the mole fraction. So we only have one unknown. The tricky thing here is that we do not have a linear equation at all, and we can't solve for temperature explicitly due to the fact that all these constants here are different. And so the way in order to solve this is you have to go to the strategy that you learned about in computations, and you have to solve equation 1 implicitly. So essentially you got to use either MATLAB or even just Excel Solver will enable you to solve for temperature there. In any case, whatever method you use, you'll find that when you solve for the temperature, you'll get that this bubble point temperature is 99.9 degrees Celsius. Right? So we have the first part of our problem solved. And for the second part, it's actually pretty straightforward from here. So once again, if we go back to Raoult's law, we know that P1 can be described in terms of its vapor phase composition times the total pressure. And from Raoult's law, we can relate that to the liquid phase composition and the vapor pressure there. The only unknown we have now, since now we know temperature, so we could plug it in to Antoine's equation, the only unknown we have is Y1. And so rearranging and solving for Y1 gives us a Y1 value of 0.46. Okay? Alright, and so, for these sort of Raoult's law problems, this is sort of the basic guideline that you would follow in order to solve for your bubble point temperature in the system.